chapter 15 is talking about the inference for regression, and we did regression way back in chapter 3. So you might need to go back, and way back actually, and remind yourself many concepts from chapter 3. I'm not going to obviously go through in detail a lot of what we covered in chapter 3, so I did attach a couple videos on some calculator steps that you may have forgotten, that you haven't used in quite a while, and I will reference those as I go through. So, review of chapter 3, because you're going to use all of this in chapter 15, is reminding you a lot about different regression topics. So when you have a scatter plot, it's going to show some sort of linear relationship between a quantitative explanatory variable and a quantitative response variable. So you're going to have x explanatory, response y, so kind of refreshing you on that. You'll have a least squared regression line, which will fit your data so that you are able to predict a y for a given x value. And that's found from your calculator, the least squared regression line. And just a little reminder of notation, it's a y hat equals a plus bx. Don't forget the hat above the y since it's a prediction equation. So if you take a look at this data, it shows the arm span and heights of 18 people. So you have different arm spans and then their respective heights. So it's just spread over several categories. So I guess maybe what you want to take away from this video is push pause right now and type all of the arm span data into like a list 1 and then maybe all the heights into a list 2, and then I'll carry on. So question 1 says use your calculator to construct a scatter plot of these data. And again, I'm not going to walk through all these steps because I have a separate video that reminds you how to do a scatter plot. So if you don't remember, I'd go back to that video. And then describe what you see. So when you do a scatter plot, depending on the data, I guess I'd remind you of a few things. You're going to need labels. So your explanatory data is your arm span, if I can squeeze an S in there, and your response variable is your height. And then some increments would be good. So I'll put a little break in my graph. If I recall, the arm span ranged from about 60 through 80. So maybe I'll say this is 60, 62, et cetera, all the way out through 80, just to give an estimate. And then same with the height in inches. We'll kind of start at 60 and go up through 80. And then if you graph it on your calculator, basically you can just kind of plot what you see. So this is kind of an estimate of the points that I see, and then describe what you see. So I'm going to remind you about describing a linear relationship is form and direction and strength, and that goes way back to chapter 3. So we have a, if you're looking at the trend of this data, it's very, well, it's obviously a positive relationship, and it's very strong, and the form is linear. So all in one sentence, I can say I have a strong, positive, linear relationship. And I'm good. So form, direction, strength. All right, question 2 says find the equation of the least squared regression line in your calculator and record that equation below. And I guess I'll remind you, I'm not sure if this is on my previous video. So 84 calculators to find your least squared regression line, you go to Stat and arrow over to Calc. And 89s, you go to F4 for calculate and then down to regressions. And that shouldn't be too far from your memory. However, make sure both calculators that you're choosing A plus BX, especially 84 calculators. You don't want to choose the AX plus B that comes first. Make sure to define any variables. You probably won't be reminded to do that, so here's your reminder to never forget to do that. Anyway, when you run your regression all on your calculator, the equation that you get is 16.4355 is my y-intercept, my A, plus 0.7672 times x. Don't forget the hat above your y. Y hat is my predicted height, and x is my arm span, and those are both measured in inches. Number 3 says interpret the slope of the least squared regression line in context to the problem. So remind yourself that slope is your change in y over change in x. So basically, if my slope is 0.7672 over 1, it's going to be an increase in 0.7672 inches of arm height, for every 1 inch in arm span. So if you think about that mathematically first, maybe before you write it out. Another key is this is going to happen on average. So I might say for every 1 inch increase in arm span, we predict, and then I'm going to squeeze in at this point, on average, a 0.7672 increase in height. Number 4 says, show how you calculate the residual for the individual with arm span of 74 and 72. So what you need to do, and you might need to go back on a previous slide here, but you need to go back to the data and look for the person that had the arm span of 74. And I'm just going to write out that full point. So that person with an arm span of 74 had a height of 76, and that was the only 74. The person with an arm span of 72 had a height of 74. All right, so a residual, I'm going to first start there, remind you that a residual is your observed y value minus your predicted y value, and the order is important, obviously, because you're subtracting. So I have my observed y values here, and that's the 76 and the 74. My predicted y values, of course, will be what I get from my prediction equation when I plug in its respective x coordinate. So I'm going to remind you of our prediction equation from the previous problem, and that was 16.4355 plus 0.7672. Okay, so you need to put in the x value, so put in 74, and pause the video and do this, okay? Put in 74 for x. Sorry, I kind of dropped my x there. So put the 74 in for x, see what you get for your y hat. Okay, and when I do that, I get, my residual is going to equal my predicted y value, which is 76. That comes from here. And then when I put 74 up into my prediction equation, I get 73.208. And again, check and make sure you get that too. So that residual, of course, if I subtract it, is 2.7917. So that means it's above my predicted value is above the, or my observed value, is above the line. For the other point over here, I'm going to put this 72 in for the x of my prediction equation. Then I'm going to take my observed y minus what I got from my predicted y. So my observed y, my residual here, my observed y is 74. And when I put 72 in for x, I got 71.6739. And that difference is 2.3261. And that point is also above my least squared regression line. Number 5 says, what would you predict for the height of an individual with the arm span of 75? So that's pretty straightforward. You just put in 75 for x, and that is 73.9755 inches, and you can double check and see if that's what you get. Number 6 says, interpret the value of r squared from your calculator in context of this problem. Okay, so when you run to get r squared, and that is called the coefficient of determination, just to remind you, not to be confused with r. R is correlation. Okay, so they are obviously connected mathematically, but not to be confused between the two. Anyway, r squared, you get, after you run your least squared regression, on your calculator, you should get an R and an R squared. If not, definitely talk to your teacher. Your diagnostics may have gotten turned off. But from there, and you don't have to calculate this by hand, you get R squared. And I got 0.8481, sorry. Let's see if I can just erase that. 8481 is my R squared. And your coefficient of determination is the fraction of variation in y that can be explained by your least squared regression line of y on x. And that's a really kind of just almost a sentence you have to memorize, and you may have forgotten it over time. So in this case, my fraction of variation is 84.8% of the variation in y, and y is height, so make sure you bring in context, can be explained by the least squared regression line of arm span I can't seem to spell today. I can't spell and talk at the same time. Least squared regression line of arm span and height. Okay, so again, go back to your chapter 3 notes, rememorize this. R squared is the fraction of variation in y, but put in context, that can be explained by the least squared regression line of x and y. So, with context. All right, so that's kind of your refresher of chapter 3. The last thing is just notation that you're going to be running across in this chapter. And if you recall, slope is b, y-intercept is a, and you probably remember that. Now we're going to be doing inference on these variables. So when you infer something about the actual slope and y-intercept, you're going to use beta and alpha. So if you look down here, slope, what you know is slope is b. So our inference, or our estimation for the population, is b, but our parameter then is beta. The y-intercept estimate that we've always used is a, so the parameter notation is alpha. So when you have your prediction equation, y hat equals a plus bx, for your parameter, it would be mu sub y equals alpha plus beta x. So that's pretty easy to remember because they're alphas and betas instead of a's and b's, so that's kind of nice. These you should know. Mean is x bar, parameters mu, variance versus its parameter, standard deviation, proportion, so that's probably nothing new to you at this point.